Hello, I'm Seema and welcome to part 40 of the chapter Hydrocarbons. In the previous video, we talked about the structure of benzene and I told you how Kekulé with a lot of difficulty finally realized that the structure, or he gave the structure of benzene according to the valence bond theory, and according to that the benzene structure was like this. It consisted of 6 carbon atoms which were bound in a ring and with alternate double bonds, and therefore he gave two structures which were identical, or two canonical forms which are known as the Kekulé structures. The first structure is where the double bond between the first carbon and the second carbon, there is no double bond. The double bonds are between second carbon, start at the second carbon, the fourth carbon and the sixth carbon. And in the second canonical structure, the double bonds start on the first carbon, the third carbon and the fifth carbon. But these were two extreme structures that were given by Kekulé. And there was a problem with the Kekulé structures, as I told you in the previous video just before finishing it, that it was found that when you carry out a dye substitution, or you substitute benzene twice to get an ortho product, according to the Kekulé structures, you should get two different products. That is one which is between where the ortho product, the two substituents have been attached between two carbon atoms which have a single bond, and another one where the ortho product should be such where the two attached substituents should be attached to two carbons which are already bound by a double bond. But it was found that the ortho products are always identical. Therefore, it could be understood that although Kekulé had given a very good explanation which seemed to be logically very correct, but chemically it was proving that these structures are not right. So the structure of benzene needed a little more study, and the explanation had to be different from this. So Kekulé just said, okay, since it seems to be pretty identical, all the carbons are, although you would imagine that the carbon-carbon single bond length is different from a carbon-carbon double bond length. So a carbon-carbon single bond length is 154 picometers and a carbon-carbon double bond length is 133 picometers. But in benzene, all the 6 carbon-carbon double bond, bond lengths are 139 picometers, which is neither as long as a single bond nor as short as a double bond. This length is somewhere between the two, and all the carbons appeared to be identical. So Kekulé said, okay, the double bond if this is one carbon, the double bond can form a bond with the neighbor on the other side, or it can form a double bond with the neighbor on the other side. And this keeps shifting, and that is why you cannot, that is how he explained that you get only one product, because of the shifting of bonds. And this shifting of bonds led to these two canonical forms which were known as Kekulé structures. Now, even this could not clearly explain what was happening. Okay, you might explain the ortho products by this. What about the extreme stability of benzene? How would you explain the abnormal stability of benzene and the fact that benzene, since it is unsaturated, it should undergo addition reactions, but it undergoes substitution reactions? So this still could not be explained by Kekulé. That was explained by the concept of resonance. So in this video, we are going to talk about that how the concept of resonance came about, and once the idea of resonance was introduced to the structure, it became very clear why benzene has those special properties. So let us start with it. Resonance and the stability of benzene. According to the valence bond theory, the concept of oscillating double bond is now explained by resonance that I just told you. So according to that, C6H6, that is benzene, is a hybrid of various resonating structures. The two Kekulé structures are only extreme structures. And the resonance can only be explained as a hybrid of many structures. It is a little confusing. What does it exactly mean? We'll understand that this particular sentence when we understand how resonance, the concept of resonance, and how it is, these two are just extreme structures and none of them actually is the structure of benzene. Now let us take carbon and the hybridization of a carbon atom when it is in the excited state. Carbon has 6 electrons. It is the sixth element of the periodic table. It has 6 electrons. In the 1s orbital, it has 2 electrons. In the 2s orbital, it has 2 electrons in the ground state. And in 2px and 2py, it would have 1 electron each. As soon as, or just before carbon is going to react, it turns into its excited state, and one of the electrons from the 2s orbitals jumps to the 2p orbital and hybridization occurs. Hybridization occurs in atoms so that you get symmetrical structures or more balanced structures of the molecules that are formed, because nature favors symmetry. So we find that in the case of benzene, the carbon, the electron jumps up, the carbon atom gets excited and hybridization occurs. But hybridization occurs not between all these 4 orbitals, it occurs between 3 orbitals. That is, one s orbital and 2 orbitals hybridize to form sp2 hybridized carbon. The 2px, 2py and 2pz. The 2pz orbital, as you see, is not enclosed in this blue box which I have made for hybridization. It is outside the hybridized orbitals, or we say that there is one unhybridized p orbital, 2p orbital. Since px, py and pz, these are just names that are given to it. They are 3p orbitals, and in order to allot them certain names, we say one is x, one is y and one is z, to tell them that they are different. But out of these 3, they are basically identical. So 2 of these are participating in hybridization and the third one does not participate in hybridization, and we call it the unhybridized 2p orbital. As a result of this, if we go to the Kekulé structure again, imagine what Kekulé would have thought. A sp2 hybridized orbital has, what is the shape of an sp2 hybridized orbital? There are 3 orbitals, 1s and 2p. So 3 orbitals are hybridizing, and if 3 orbitals are hybridizing, imagine what would be the structure in which they could stay as far apart as possible. They can stay as far apart as possible if they occupy, these 3 bonds occupy, the ends of these 3 bonds occupy the 3 corners of a regular triangle, right? So sp2 hybridized orbitals, they have this shape, that is a triangular planar shape. Since benzene was imagined to be a ring of 6 carbon atoms, all the 6 carbon atoms are sp2 hybridized. And all the 6 carbon atoms are forming this triangular planar structure. And look at this, this is a carbon, it forms one bond with this carbon, one bond with this carbon, and one bond with this carbon. So all the 3 sp2 hybridized orbitals are forming bonds. In every carbon, they are forming bonds with 2 neighboring carbons and 1 hydrogen. Look here, this carbon is forming one single bond with this carbon, one single bond with this carbon, and one bond with hydrogen. Similarly, this carbon is also doing that. One with carbon, one with carbon, one with hydrogen. One with carbon, one with carbon, one with hydrogen. And if I keep moving this, you'll get one with carbon, one with carbon, one with hydrogen. Every carbon is forming 3 bonds. 2 with the neighboring carbon atoms, 1 with hydrogen, and each one of these forms a triangle. If I want to make, I could make a triangle for each one of these. Just to show. Look, if you join the hydrogen, the carbon, and this. So this carbon is sp2 hybridized. It is forming 3 bonds in such a way that they fall on the 3 corners of a triangle. Similarly, this carbon is also forming 1, 2, 3. Do you see it forms a triangle? So sp2 hybridized carbons, each one is an sp2 hybridized carbon. Each one is forming 3 bonds, 2 with the neighboring carbons and 1 with hydrogen. So it forms, this entire structure is planar. Since it is a planar, triangular planar, this entire ring is a plane. It is, you can actually make it in 2 dimensions. If this was an actual molecule, it could actually exist like this on the board. But there is one unhybridized orbital. And we know that p orbitals are the shape of a dumbbell. Right? We know that the shape of a p orbital is that of a dumbbell. Now imagine I have this hexagon that I had made for some other lecture, but this is the shape of the benzene ring. The benzene ring is hexagonal. All the carbon, and it is planar, it is very symmetrical, although when we make it slightly longer when we make it on the board, but it is actually very symmetrical. So each one of the corners is a carbon, the carbon forming two bonds with two carbons with one hydrogen, two bonds with two carbons, one hydrogen, two bonds with two carbons, one hydrogen, the same thing that I explained to you. So it is a very planar structure. But the unhybridized p orbital is like a dumbbell. Here I have a dumbbell. And the unhybridized orbital, since it is like this, it is perpendicular to the plane of the molecule. Since it is perpendicular to the plane of the molecule, you will imagine a dumbbell at every carbon atom. Half of it coming forward, and half of it going back in the back. All 6 carbons have these dumbbells. The unhybridized p orbital is in the form of this dumbbell. So you can imagine one ball, the ball here, and you have 6 of them on every corner. So when you look from the front, you will not be seeing this. You will only be seeing these 6 dumbbell heads. And these 6 dumbbell heads will, if you have one, imagine this is also actually the shape of a hexagon. So these 6 will appear to be forming a ball, like a circle, and then a ball here, whole 6, and all 6 of them, the carbon atoms in between. And these 6 together, 1, 2, 3, 4, 5, 6, will together be forming something like a donut or a bagel, like I have this bagel. So the bagel is nothing but the p orbitals in front, the p orbitals in the back, the other half is the other half dumbbell, because what you are seeing is 1, 2, 3, 4, 5, 6. Together they'll give the look of a bagel or a donut. So imagine that this, I'm making a sandwich of paper. Okay, imagine that this planar structure is between these. So you will imagine the structure to be something like this. That the unhybridized p orbitals are forming the bun up here, the bun down here, and the hexagonal structure of carbon and hydrogen ring is in the middle. Now, let us come to the orbital structures. Why do I imagine this to be? Look at these structures. The 6 carbon atoms are 1, 2, the centers are the 6 carbon atoms. The dumbbells that you see are the unhybridized p orbitals, which are perpendicular to the plane of the benzene ring. Now, this is a structure that it's a 3-dimensional structure that has been made on a 2-dimensional board. So it appears like this to you. Actually, I've tried to show it to you like this, right? The planar structure is like this, but since it is in 2 dimensions, we are showing it to you slightly tilted like this. So you see the 2 dumbbells here, up and down, above and below the plane, this above and below the plane, above and below the plane of this, above and below the plane of this, and above and below the plane of this. So now we are trying to show you the structure like this, and then if you carry out the bonding like Kekulé did. Kekulé, what did he imagine? He imagined, okay, these 2 have unhybridized p orbitals have got 1 electron each. Every carbon has 4 electrons in the outermost shell, right? In the 1, 2, 3, 4. 3 have already bound, but each carbon is left with 1 electron. This is the wrong pen. Okay. Each carbon is left with 1 electron. So the 2 electrons between this carbon and this carbon, this carbon and this carbon. Each carbon has one. I should actually make it right under it so that it is not confusing. Every carbon has 1 unhybridized p orbital electron. Do you see this? So these 2 carbons, they can form a double bond here. These 2 can form a double bond here, and these 2 can form a double bond here. That is how Kekulé imagined his structure. He said that benzene is a structure of cyclohexatriene. That it is a cyclic hexa, 6 carbons, triene, there are 3 double bonds, 3 enes. and these enes are alternate double bonds. If he had imagined that these two carbons form the double bond here, then the structure would have been the other Kekulé structure. You can imagine this to be either these three bonds, or you could imagine them to be these three bonds. If why blue, it should be a color that will be visible. So let me get red again. If these two carbons had formed the bond, you will get the other structure of benzene. These two, then these two, and these two. So if you imagine the red bonds, you get one structure, one Kekulé structure, and if you imagine the three black bonds, you get the other Kekulé structure of benzene. That is how Kekulé imagined his molecule. And this is how when you give the orbital structure, this is what appears to be to us. That the structure should be something like this. Now going ahead, I told you that scientists had now realized that this was a very symmetrical structure. The benzene ring was a very symmetrical hexagonal ring. And according to bond lengths, the carbon-carbon single bond length should be different, carbon-carbon double bond length should be different, but all the bond lengths were equal. What did this explain? Since all bond lengths were equal, it was now imagined that these bonds, these electrons in the p orbitals, which are above and below the plane of the structure, these electrons they do not form double bonds as such. They do not form double bonds with one neighbor, and the alternation of the double bonds does not take place. You can imagine that you have two friends. One friend is, and both of them are equally likable to you. You like both your friends equally. So you three are sitting, and you are sitting in the middle. One friend is here and one friend is here. What will you do? Imagine, what would you do? Would you just talk to one friend and form the bond only here and not talk to that friend, while actually that friend is equally dear to you? So obviously what will you do? You'll talk to this friend and you'll talk to this friend. Sometimes you'll talk to this friend. Sometimes it'll be almost equal, because you like both of them equally. So that is the situation. All the carbon atoms, since they are symmetrical, the carbon cannot decide whether to give its electron or share its electron with this neighbor or with this neighbor. With this friend, talk to this friend or talk to this friend. So what happens is that it doesn't, when you are talking, you don't count, you can imagine in life, what do you do? When you're talking to two friends, do you count? Okay, I spoke to this friend once, now it is this friend's turn. Now it is this friend's turn. You don't do, conversations don't go like that. You just talk, you're just talking, all three of you, and you don't even feel, very naturally, you move from one to the other. If four more, or rather, you are three friends. If three more friends come in and you sit in a hexagon, what would you do? You'll talk to all five of them, isn't it? You'll be talking to the neighbors, you'll be talking to that person. So what is happening now? If your talk is the electron can literally move, they become delocalized. Your friendship or your love is not located here. It starts moving between everyone. So that friendship or that love starts moving. The electrons, similarly, the pi electrons or the electrons of the unhybridized p orbitals, they do not get stuck between three carbon atoms. They start flowing between all the 6 carbon atoms. The term that we use for this is that they get delocalized. There is no location. You cannot now tell an electron is just an electron. Love is only love. If that person loves you and that love is also flowing, can you tell, oh no, this is my love and that is his love? Love is love. That friendship is friendship. It's just friendship. It is just happiness. It is just joy that is moving around between all of you. So similarly, the electrons, once they get delocalized, you can't tell, okay, this is my electron, that is his electron, that is her electron. You can't do that. They are just electrons. They are just joy. They are just friendship. And what does joy, friendship, love do? It binds you together, right? It binds all of you. You become a group. You become very stable. You become strong together. That is what happens. in the case of benzene. These electrons, they become delocalized, and all the carbon atoms love those electrons equally. They don't say this is mine. Any electron that is coming is just friendship, it is just love. You don't say this is yours, that is mine. So the electrons are shared equally by all 6 carbon atoms. And since they are shared equally by all 6 carbon atoms, this imparts a special kind of stability to the molecule. And it is this stability that is imparted to the molecule and this phenomenon is known as resonance, that the electrons get delocalized. They don't stay between 2 or 3 carbon atoms. It becomes totally delocalized. This is known as resonance. So now let me just read this. According to valence bond theory, the concept of oscillating double bond is now explained by resonance. Benzene is a hybrid of various resonating structures. Now do you understand this dotted line? That the electrons of the unhybridized p orbitals are not localized, they are totally delocalized and belong to all 6 carbon atoms, and which can either be shown by this dotted line, the dotted circle, or just a proper circle. After all, they are all electrons and they belong equally to the entire molecule, to all the carbon atoms. So that is how the structure of, if these are the 2 Kekulé forms, if we make the orbital structure, in Kekulé forms, the bonds are between these 2 carbon atoms, the double bonds between these 2 carbon atoms and these 2 carbon atoms. And in this Kekulé structure, the double bonds are between these 2, and these 2. So they are localized. But in the hybrid or in the resonance hybrid, they are delocalized. So we show that all of these p orbitals on the top, the entire dumbbell on the top is electrons that are forming an entire dumbbell. In the middle, you have the carbon and hydrogen. In the middle, you have the carbon and hydrogen network. And on the other side, you have the other side of the dumbbell of the entire unhybridized p orbitals. And now that the sandwich is formed, imagine, is addition reaction possible here? Only the hydrogens which are dangling on each corner, they will be substituted. They are so stable, they are not going to allow the bond to be broken because there is no double bond, proper double bond. They are all hybridized and the friendship is too strong. So only substitution reactions take place and addition reactions do not take place in the case of benzene. As I told you, the bond lengths again points to, remember, the bond lengths, if they were single and double bonds, alternating single and double bonds according to Kekulé should be different. But in the resonance hybrid, it was found that it is actually found in benzene that all bond lengths are 139 picometers, which are between these 2 lengths, which also supports the concept of a resonance hybrid. All the 6 carbon atoms of benzene are sp2 hybridized. 2 sp2 hybrid orbitals of each carbon atom overlap with the sp2 hybridized orbitals of the adjacent carbon atoms to form 6 carbon-carbon single bonds, which are in a hexagonal plane. Now you understand all of this, you know. Each carbon forms 2 sp2 hybridized orbitals of each carbon form single bonds with the adjacent carbon atoms. And the remaining sp2 hybridized orbital with every carbon forms a single bond with the hydrogen. And hydrogen has only s orbital, so it forms an overlap, a sigma bond with s orbital of hydrogen to form a sigma bond. Then the unhybridized p orbitals on each carbon are close enough for a pi bond. Each of these are the dumbbells is close enough to overlap on the side and form a double bond. Where's the second dumbbell? Yeah. If you imagine these 2 on these 2 carbon atoms, they are so close that they can overlap. And if they overlap, they can form a pi bond, and there are 6 of them. 1, 2, 3, 4, 5, and 6. So close to each other. So they can also overlap and form the bond. So they do. The unhybridized p orbitals on each carbon atom are close enough for pi bond, but the internuclear distance between all the carbon atoms is the same, which is 139 picometers. Since the internuclear distance between all the carbon atoms is the same, the distance between all the dumbbells is the same. And this has been seen. We have verified it by X-ray diffraction studies. Through X-ray diffraction study of the molecule, we know that the bond lengths are equal, and therefore all the dumbbells are equally distant from the neighbors. So, but internuclear distance between all the 6 carbon atoms is the same according to X-ray diffraction, which shows an equal probability of overlap on both sides of the carbon. What does this show? It shows that the probability, the chances of forming the overlap is equal on both sides. The 6 pi electrons are, but what happens? They don't form solid bonds. The 6 pi electrons, they decide we are just friendship. So why do we have to stay here and here? Let us just talk among all 6. Let's just move around. Let it flow. So the friendship, the love, the joy, it flows. And the electrons, they flow. So the 6 pi electrons are delocalized and now can move freely. These pi electrons are attracted more strongly by the carbon nuclei. Now all the carbon nuclei, all of them have 1 electron, and they have just given off that 1 electron. So they love all the 6 electrons equally and rather strongly. So they attract them more strongly by the carbon nuclei, and the presence of delocalized pi electrons makes benzene more stable than Kekulé's cyclohexatriene, right? So this is how, with the help of resonance, it was explained that these delocalized electrons, the carbon nuclei that of the entire molecule of all the 6 carbons, they attract these electrons more strongly, and that is why they make the molecule so stable. And that is why, due to resonance and the similarity, due to resonance you have the same bond length, therefore you get the same ortho product. Due to resonance, there is more attraction between the molecules, therefore you have there is more attraction between the carbons and all the electrons, therefore you do not have addition reactions, you have substitution reactions in benzene. It does not show addition reactions like in unsaturated hydrocarbon. So this was resonance and the stability of benzene. With this, I'll wind up today's video. If you wish to watch the other videos of this chapter, please click the link that will appear on top of your video. And if you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.